Good afternoon, Science Theatre. How are we doing? Very, very quietly once again. Good grief, what is up with you guys? How you doing? One fantastic, a couple of sad groans from the rest of the room. Once again, my name is Shashank. I'm with you because we sent out that search party for Andrew's voice, and someone turned in some broken code, so he's still trapped in another time zone. Today, however, we're going to talk about something almost completely and totally different to anything we've really been talking about. Up to this point, we've seen a lot of C syntax, a lot of how to make things happen. We'll talk a little bit more about structs in a moment, but the majority of today will be talking about this amazing phenomenon that happens when I take any set of really, really simple rules. They don't have to be particularly complex. Any set of nice, simple rules will reproduce the results I'm looking for here. And as I just frantically rescue a demo, I want to show you one of the challenge exercises, a solution to that challenge exercise. If it works, it was momentarily not working. There it is. This is the life activity. It's going to run out of steam in just a moment. I will just tweak that to turn the number of generations up. Yeah, I might make it just a tad bigger as well. How big is my terminal here? 159 by 37. 159, let's say 30, that'll do. And we'll set that to go for a little bit longer. That should keep it going for a bit while I talk a little bit about what's going on here. That's better. All right, so behind me you can see this is a little thing called Conway's Game of Life. And it looks like it grinds to a halt fairly quickly, but all that's going on here is that I'm taking a really simple set of rules. Oh, it's ground to a halt. I've got a really simple set of rules in here, in this system. I've got these cells in this big two-dimensional grid. Every single cell has two states. It's either alive or it's not. And a cell goes from being alive to not being alive if it's overcrowded, if there are more than 3 live cells around it. It also remains not alive if there aren't any live cells around it. It comes to life if there's 1 or 2, exactly 3 live cells around it, excuse me, and other than that, the cells will die. And so what you can see here is if I apply that rule to every single cell, and then I flip to the next generation, and then I apply that rule to every single cell, and then I flip to the next generation, and I apply that rule to every single cell, and I display this, what you can see is, in this case, they're just flipping backwards and forwards, but you saw at the beginning, and I'll just restart this, you can see there's a lot of complexity going on there. And you wouldn't think from effectively 2 or 3 really simple rules that something quite so beautiful and complex can emerge. And that's really the whole theme of what we're going to be talking about today. We're going to write some programs to explore the notion of emergent complexity. It's things that are in a system where the rules are so simple, it doesn't seem like there's any reason for that complexity to appear, and yet it does, and it's beautiful. So what we're going to do to start off, we're going to play with numbers. Numbers are nice and beautiful, I think, and they're really a beautiful place to observe why things behave in this way. So I'll just blow my terminal back up to a slightly larger size. This is a really interesting phenomenon. I'm going to call it wondrous.c because it is so, I think, beautiful and wondrous. And what it is for any number, for any positive integer, I have a very simple rule. If that number is even, I halve it. If that number is odd, I triple it and add 1. Yeah? And we know how to write a very simple C program to do that. And so I can put in a set of rules, I can encode this set of rules. And the way that would look would be an if statement that takes some number. So before we get right down to the nitty-gritty of that, though, let's talk about how we would approach the function aspect of this, because this complexity comes out of this notion of a very simple function that changes its input. And we've seen functions that are simple, that change their input, that perform one small unit of work. So if I were to write such a function, and I'll just quickly write out all of the boilerplate that you need for a program. Today being, of course, the 30th of August, while I just quickly whip all of that back, all of the boilerplate out, I also should quickly mention just some comments about administrative work. The assignment 0 provisional marks have been updated, and some people's marks have actually gone up. It's really quite impressive. We've fixed up a few little things, but this is just your correctness mark, still just changing. There's some fewer tests that have caught a few people out in really, really bad ways that we've fixed up there. If you think, by the way, that you submitted a valid unit test and you don't seem to have a valid unit test on file, please email Andrew, because we do want to actually make sure you get that you wrote a valid unit test. Yo! Yep. Yes, if you have a valid unit test, you'll be able to see whether we count that unit test or not. If you think you submitted one that's valid but we didn't count it, please let us know so we can fix that up. Oh yes, and milestone 2 is due tonight. So if you haven't yet come up with a submission for that, that is a good thing to do. And have a look back at how you've gone over the last week or two into assignment 0. Also, on the topic of the date, tomorrow is Census Day. If you're feeling a little bit uncertain about how you've been progressing in the course, have a chat with your tutor. They're sort of best placed to answer questions about how you're going in the course. Oh, and yes, if you can't see your marks in WebCMS 3 at the moment, yes, we know there is an issue with WebCMS 3 at the moment that's causing marks to not be displayed, but you can run the commands that we announced earlier today, 1511 class run check and then the activity name, or 1511 class run sturec to get your marks, or alternatively go to give online. Okay, so let me just check that I don't have anything else that I've missed on my list of things that I have been sent to talk about. Good, okay, we're up to date. Cool. Back to this wondrous number thing. So we know what the rule is, yeah? Let's say we've got some number, we'll call it n. We've said it's going to be a positive integer, which means we can fairly happily store this in an unsigned int value. So you can store it in an int or in an unsigned int. Doesn't really matter. I'll go with an unsigned int for now. And I'll call it n. You can call it really whatever you like. In fact, we'll call it number. And we know that our rule is very simple. If number is even or if number is odd. How do I tell if a number is even or odd? I hear muttering of modulo 2. That is absolutely spot on. So I would take the number modulo 2, the remainder after I divide it by 2. If that's 0, the number is even. And if it's 1, the number is odd. So I'm going to say if number modulo 2 is 0, then I'm going to say number is. So number is even, number is halved. Otherwise, number is 3 times itself plus 1. Yeah? This is a really, it's like you look at that and you go, that's very simple, just sort of, these are so incredibly simple as rules. We have a rule that says number is half of it, or we triple it and add 1. Yo! Yes, but we'll play around with that in a little bit more detail. For those of you who have a mathematical bent and you've already spotted where we're going, I think this thing is beautiful and we are going to play with it. I don't really just want to skip over this. But here it is. This thing takes a number, applies this rule to it. We want to do this more than just once, though. If I were to do this just once, it wouldn't be all that interesting, yeah? If we saw that demonstration of life from earlier, and in fact I'll show you what that looks like if I just do it once, it's not interesting. You can sort of see something happens, but there's nothing particularly interesting going on there. So instead what I'm going to do is I'm going to take this and I'm going to apply it again and again. And this is the thing about these patterns where you have a simple set of rules, but they change the numbers you're playing with, or they change the inputs you're playing with, such that there is a subtle but beautiful change which expands. So what I'm going to do is I'm going to take this code and I'm going to put it in a function. I'm going to call it wondrous. And I'm going to just say wondrous of number. And it's an unsigned int function. It takes an unsigned int. It returns an unsigned int. And it, of course, just returns number. I actually had a really interesting question just before I go on too much further about this sort of construct and what's going on here. I've been given number as a variable. It's come in from the outside world. So nominally, is it okay to change the value you're given? Yeah, it is. It's relatively okay in this way. Because what we're given here, we're not given a pointer, there's no references going on. This is just a number. Yeah? I've just given us a number, and so we can take that number and change it, and then give it back. And this is a way we can apply a number again and again. And apply a function to a number again and again. This won't change the value of number that we have in main until I do number is wondrous of number. I'll grab this. Whoops, that is the wrong key. I'll grab that. I'll pop that up there as a prototype. There it is. So this will compile, this will run, this won't do anything interesting yet. What I'm now going to do is I'm going to read in from the user an input. I'm just going to ask the user for their favorite number. We know some obvious favorite numbers rather from in the room, so we might get a few other ones and play with them. I'm just going to read in a %d for now into number. I'm having a very bad feeling about the unsigned at the moment. I think we'll just drop the unsigned for the moment, just to keep it less alarming. Okay, so we take in a number from the user. We can apply this function to it. And now we'll print it out. This isn't going to be all that interesting. So there we have it. We have a very simple program, takes a very simple function, takes one step, and gives us back our number. So I'll just give it a number arbitrarily off the top of my head. Let's say 4. After one step, that goes to 2. After one step, 2 will go to 1. Some other favorite numbers from the room from last time. 42 will go to 21, because of course that's an even number. Another favorite number we have in the room, 17, that goes to 52. That's now even. So I could take that number, take it a step, that goes to 26. I take that a step, that will go to 13. I take that a step, that goes to 40. I take this a step, this goes to 20. 20 goes to 10. 10 goes to 5. 5 goes to 16. 3n plus 1. 16 goes to 8. 8, we can do this in our heads at this point. 8 goes to 4. Goes to 2, goes to 1. And 1 goes to 4, goes to 2, goes to 1. Goes to 4, goes to 2, goes to 1. And this cycle, 4, 2, 1, 4, 2, 1, 4, 2, 1, will continue forever, once it gets there. So, we've seen that we can take a number one step. That's really not particularly interesting, and I have to keep running our program again and again and again to get this thing to behave in the way it does and to start making observations about it. We are curious people. We want to explore ourselves. We want the program to do some of the hard work for us, more of the hard work so we can play around with what's going on. So instead of just running one step, we're going to keep running it until it reaches 1. Yeah? We're going to keep taking number to wondrous of number. Again and again and again. And of course, the way we do that is by looping over number. So while number is greater than 1 or is not equal to 1, we'll take number to wondrous of number. And because we want to have that output just a little bit more condensed, let's just print that out by itself. Yeah? So we're going to print out the number, we're going to take the next step, and we'll just keep doing that again and again and again. And at the end, I'll just print out that we're done. Yeah? Let's recompile that. And if I now put in one of these beautiful numbers like 17, we see the 17 goes 17, 52, 26, 13, 40, 20, 10, 5, 16, 8, 4, 2, finished. Let's put that 1 on the end just to make sure that we don't miss out. We'll just say 1 at the end. Okay, what's another number that we know? There's quite a few numbers, citation needed. 497. Because 1492, 746, 373, 1120, 562, 80, 140. So we can see this number sort of bounces around in ways that we don't expect. Let's play with the really small numbers first, actually, before we go off into these really big numbers. 1, of course, will immediately stop. 2, 2, 1. 3 may not do what we expect. 3, of course, will explode out. 3, 10, 5, 16, 8, 4, 2, 1. 4, 2, 1. 5, 16, 8, 4, 2, 1. 6, 6, 3, 10. And you can see that there's these patterns starting to emerge in the numbers. What I'm curious about, though, how many steps does this take? How many steps will it take for this sequence to reach 1? How many times do I have to apply this rule? We can count that. We know how to count this. So I have steps. I'll say steps is 0. And I'll say steps plus plus every time we take a step. And we'll say that we took that many steps to get to 1. Okay? We'll compile. We'll run. And now if I say, ah, yes, that 497 again takes us 22 steps. Actually, let's look at some of these smaller numbers again. 1, 0 steps. 2, 1 step. 3, 7 steps. What? How did it take 7 steps? Where did all of those numbers just spring from? If I pick another number like, I don't know, 9, suddenly I've got 19 steps. Where are these numbers coming from? Why? I mean, we've got this really, really beautifully simple rule. And this beautifully simple rule we just apply again and again and again. There's no magic in there. So where are all these numbers coming from? Why?
Is the pattern that they're themselves plus 1?
Yeah, so we can grind down our rule. We can go, oh, yeah, I suppose it's 3n plus 1, that there's something crazy going on there. But somewhere in this system of rules, somewhere in this very simple rule, we have this strange effect of numbers just not really terminating, numbers going on for way longer than you would expect. So this is rather strange. I want to briefly talk about something just to make this easier. So we ask the user for their favorite number. I don't really feel like asking the user for that number every time. I, being a lazy person, being a programmer, I can get this program to start at 1 and print out how many steps that took. Start at 2, print out how many steps that took. Start at 3, print out how many steps that took. And perhaps I could look at that. So instead of printing out each number as I reach that particular number, let's print out just the number of steps it takes. And we're going to start at some number. Whoops, number is start. So let's pick a starting number then. Let's pick a set of starting numbers. Let's loop over those. So we'll start at 1 and say, I don't know, well, start is less than 10. Let's look at the first 10 numbers. And of course, to make a loop go, there are sort of 3 things we need to make this loop happen. We need to set something, we're going to check that, we're going to do some stuff, and then we're going to step the loop forward. to the next iteration, the next pass, to work out what's going on here, yeah? So what we're doing, we're starting at 1, we're going, how many steps does this take to converge back down to 1? Then we go to 2, how many steps does this take? And we're going to keep doing that. And this will save me, of course, typing out this madness. So 1 takes 0 steps, 2 takes 1 step, 3 takes 7 steps, 4 takes 2 steps. There doesn't look like there's any rhyme or reason to the number of steps it takes. It doesn't look like there's any rhyme or reason to what the numbers are that we reach along the way. We've hidden those for the moment, but I can turn them back on, and let's have a look at them as we go. So at each time we make a step, we're going to print out that number. And there they are. So from 1, of course, takes 0 steps. From 2, we go 2, then 1. From 3, we go 3, 10, 5, 6, 4, 5, 16, 8, 4, 2, and then we reach 1. And that takes 7 steps. And we keep doing this, and somehow with 9, we've got 9, then up to 28, and then that's bounced back down. Then we've gone back up to 52, and then that bounces back down. That goes up to 40, and then that bounces back down to 16, and that bounces back down, and that takes 19 steps. So 10, that's quitter talk. Let's look at some bigger numbers. Let's look at the first 100 of these. And I hope some of you are starting to already see just how wonderfully beautiful and bizarre this sequence of numbers is. And every time I start playing with this, I get this weird chill of what is going on here. Why do we have this number of steps that just sort of bounces all over the place? There are some big numbers starting to show up here, but let's scroll right back up to the top, where the numbers are a little bit more reasonable. At 11, we go from 11 to 34, then 1752. These numbers just bounce around. It's like you've put some ping pong balls into a dryer and tried to work out what's going on. They're just bouncing around, up and down, up and down. And all we're doing is applying this very, very simple rule, and we're getting some very beautiful, complex, and strange results out. So we see you can almost see a graph there of the length of the number of steps it takes going across the screen. This one takes, obviously, 0 steps. This one takes 1 step, then 7 steps, then 2 steps. And you can sort of see this bouncing up and down. And there's no pattern, there's no rhyme or reason to the shape of this. Powers of 2, of course, well, they're just going to divide by 2 all the way back down. So 1, 2, 4, 8, 16 will all just have very small numbers of steps, but every other number will just bounce around in really strange ways. Here's another strange phenomenon. We look at, say, 14, say 15. Both of these take 17 steps to get back down to 1, but they take extremely different paths to get there. So from 14 we go 14, 7, 22, 11, 34, 17, and we bounce up and down that way. But from 15 we go 46, 23, 70, 35, 106, and these numbers just bounce around. It's mad, but we still take 17 steps. What is going on there? There is this strange complexity to these numbers, to these patterns. We didn't put that there. So where has the complexity come from? Somewhere in the system there is something beautiful and strange going on, and it's just these simple rules. And this is what we're going to play with a lot for the next few weeks. Very simple ideas, very simple rules, giving us beautiful and strange results. I have another little example up my sleeve. This is actually an example I wrote last semester in a tutorial for one of my 1911 classes, actually. And let me see if that example is still something that works. Yes. Marvelous. Cool, so I've got another very simple little example. And we can, oh yes, we saw those smaller numbers. The larger numbers, of course, are taking hundreds of steps to converge. Just as I set up this next example, here's a little thought experiment. If I throw a number at this, I just pick any number out of my hat. How many steps will that take to converge? How many steps will that take to reach 1? Is there some relation from the number to that? We can sort of make guesses here and there. If it's a power of 2, it'll take the log base 2 of that number to reach 1, because of course we just keep halving it. But for a number like 97 up here, there it is, 97, all 118 steps of it. What? Where have those numbers come from? This is madness. Why? Where? How? What is going on? Where is this beauty coming from? These numbers are also, if you were to graph these numbers individually, they bounce around in patterns that are absolutely bizarre. And the most interesting thing about this, a gentleman by the name of Collatz posed this question. And I pose it to you. If I give you any number, any positive integer, can you tell me that every single one of those positive integers will converge to 1? You say yes. We actually don't know. This is indeed one of these really, really interesting questions. It's not one of the million-dollar questions, but it's certainly a question that we don't have an answer to. Mathematicians are still puzzling over this. Where is this complexity coming from? How many steps will any given number take to converge? Do all of the numbers converge? And all that's coming into this system is such a beautiful, simple rule. If the number is even, we halve it. If the number is odd, we multiply by 3 and add 1. Yeah? Very strange, very beautiful, and really, really unexpected. Was anyone really expecting something so strange to come out of something so very, very simple? I wasn't. I really, really wasn't when I first saw this. Whoops, that's that. Let's have a look at another program. Here is a very simple program. Those of you who are paying attention in challenge exercises may spot this as being a bit familiar. This one is very, very similar to, but not quite the same as, the cellular activity. And there's this interesting field of research around these interesting, strange creatures, cellular automaton. They have very peculiar habits. If I have a one-dimensional cellular automaton, again, little creature living in memory, the same sort of thing as we saw with life. It's got 3 cells that are around it, and those say whether this cell is alive or not, from generation to generation. I'm going to pick a number like 30. Yes, 30 seems like a nice number. And I'll just briefly turn off the rest of this code just before I get there. Let's turn all of that off and return out the end. So here's an interesting little thing. Rule 30, for those of you of a binary bent, you will spot, of course, these rules come straight out, the rule numbers, excuse me, come straight out of binary representations. So, of course, the first of these rules is that no cells above me are alive, I'm not going to be alive. One cell above me to my right, I'm going to be alive. One cell directly above me, I'll be alive. Two cells, one above me, one to my right, I'll be alive. One cell to my left, I'll be alive. But again, we now start flipping to these rules where I now am not alive, where there's a cell above me to my left, to my right, I'm not going to be alive. If there's cells above me and to my right, to my left, excuse me, I'm not going to be alive. And if there's three cells around me, I'm not going to be alive. And again, very simple rule. I look at an array, I look at the cell at this index -1, at this index +1, and that determines the state in this cell at this generation. So if I now were to turn on this code that I have just turned off. And the reason this variable is called bus is because I pose this to my class as, imagine we have this very strange bus that's, say, 80 people long, and occasionally a group of people sit down. A person sits down exactly halfway along this bus, and then some people get on or get off the bus at that particular point. Oh, I did save that. I didn't save that. Don't forget to save your work before you compile it and see what happens. Once again, a very, very simple rule. Depends not on one value, but on three values. And it produces this strange complexity. We've actually done some analysis on this over the last few years and found that this is effectively entirely random. There is no way to really predict. This is like in maths, if you consider functions like sine. Yeah, you put a number in, a number falls out. But if I try taking that function the other way, it is much, much harder. This is the sort of thing where if I put some simple values in, something strange and beautiful and complex comes out, but I can't really go backwards. It's very difficult to go backwards, and with the game of life that we saw earlier, it is still extremely difficult to go backwards. You can't take these sort of systems and step them backwards. Let us change this rule number. So instead of rule 30, let's have a look at, say, a different number, rule 110. And I'm just picking numbers out of my hat, well, not quite just randomly out of my hat. And the rule here is so very simple. If the cells directly above me and to my left are alive, I'm alive. If the two cells above me to my left, to my right are alive, I'm alive. If the cell directly above me and to my right is alive, I'm alive. If the cell directly above me or above me and to my right is alive, I'm alive. Otherwise, I'm not. I seed it with one cell of life. And you can see that step by step, this complexity emerges in the system. I didn't put that complexity there. I have nowhere in this system hidden a triangle. If you look through my code, there are no triangles up my sleeve. Let me try a different number. Rule 17. Once again, I've seeded it in one spot with some life. And for those of you who can do your binary very fast, if there's nothing alive above me, I become alive. If there's one cell above me to my left, then I'm alive. Otherwise, I'm dead. And you can see we have this strange flipping backwards and forwards from row to row. But also there's this strange line that is drawn across the grid. I didn't put that line there. It has come out of the rules of the system. It's very strange and very beautiful. Let me try another one. Rule 18. Once again, I've not put any triangles in here. The triangles just appear. This is worse than HSC maths because we don't know where the triangles are coming from. The triangles are just appearing and I'm not putting them there. They are a side effect of this very simple rule that we apply again and again and again. Yeah? This seems like a good spot to pause while you are all thinking and mind-blown about these strange and wonderful creatures that appear out of the most simple rules. So we'll take a brief break. We'll take, judging by the number of questions I'm going to get, probably about 10 minutes. We'll have even more of these strange rules coming up after the break. We're going to have something that looks beautiful as well. So stick around.